In part 1, we found arc length along the basic parabola y equals x squared. For this part, we want to find arc length along the general parabola y equal to a quadratic in x. Now, our specific problem, find the arc length along the parabola y equals 1/10 x squared minus 1/10 x plus 20 from x equals 0 to x equals 20. Main trick here, we're going to have a parabola with its vertex somewhere in the plane. We'll use completing the square to move our vertex to the origin. Then we'll be able to apply our result from part 1. Now, first part, I just want to shift my parabola to the origin. So note, if I have some arc along the parabola and I want to find its length, if I shift our parabola vertically, we'll have no effect on arc length. If we shift horizontally, no effect on arc length. So we'll just need to do the bookkeeping to make sure we get the right answer. Now, the way I'm going to shift is to first complete the square. So the idea is I want to take our 1/10 x squared minus 1/10 x, complete the square here, see what comes out, and then we're going to remove all the shifting. So the idea, if we complete the square on this first part, we have 1/10 quantity x minus a half squared minus a quarter. We put our 20 back in. Then we note, okay, our vertical shifting, that's just adding constants to our function. So if we remove those, we're going to put our vertex on the x-axis. So I can remove the 20, and I can remove the 1/10 minus a quarter. So that'll leave me with y equal to 1/10 x minus a half squared. To get rid of, okay, our horizontal shift, I'm going to let u be equal to x minus a half. That's going to move us to the origin in the uy plane, which is just as good. So there we'll have y equals 1/10 u squared. Okay, we're doing our substitution, u equals x minus a half. That means our limits of integration are going to go to minus a half and 19 and a half. So with this, we've taken our parabola and we've just shifted to the origin. We have a nice function, and the only penalty is we're going to have to use different limits of integration. Next step, we apply our arc length formula to our data in U. So we have our function, we have our new limits of integration. For our arc length formula, I'll need the derivative of y with respect to u. So if y prime is equal to 1/5 u, we put everything into our arc length formula. So we'll have the definite integral from minus a half to 19 and a half, square root of 1 plus 1/25 u squared with respect to u. Now, all the heavy lifting is done in part 1. So all of our work went into finding this antiderivative. So I just want to find a substitution that's going to carry 1/25 u squared to 4x squared. Okay, and here we'll recycle the x variable. So I'll let 1/5 u be equal to 2x, then u is equal to 10x, and du equals 10 dx. Now, in our substitution, we want to wind up in terms of x. So we'll have the x of minus 1/2 is equal to minus 0.05. X of 19 and a half is equal to 1.95. Now, we substitute. That gives the following definite integral in x. If I pull the 10 out, we can apply the fundamental theorem of calculus. So we have the antiderivative from the previous board. So we get 10 times f of 1.95 minus f of minus 0.05. If we run this through a calculator, we get 44.93. So that's our answer for arc length. Now, we check our answer. So we'll have 2 checks, and in both cases, we're going to go back to the original data. So we're going to have our original equation of the parabola and our original limits. So going from 0 to 20. If we sketch the parabola, okay, I can connect the dots if I take the endpoints and draw in the lines that are parallel to the x and y axes to get a right triangle. First thing, we note if this is drawn to scale, then our arc length is going to be less than the sum of the lengths of the legs on the triangle. So we'll have 20 and 38. So our arc length should be less than 58, and that bears out. Also, the arc length should be somewhere in the ballpark of the length of the hypotenuse. If I work that out, I get 42.9. So we see that's also going to bear out. Okay, so that's not a great check, but we know we're not off by an order of magnitude. Now, if I want a concrete check, I'll use a Riemann sum. So here what I'm going to do is, we're going to take the element for arc length for the original function. Okay, I'll sketch that. Our limit goes from 0 to 20. Then we're going to fill in this area with rectangles. So I'll use base length 0.001. Then I can code this into my computer, and what will come out is 44.93. So it's going to be our approximation for this area. Okay, we note this is coming out to be our answer over here. So I'm convinced that we have the correct arc length.